Okay, hello everyone. Welcome to the MIT Category Seminar. Today we have Mike Shulman, who's going to talk about conservativity of duels. Hi, Mike. Welcome.
Hello. Thank you. And thank you for the invitation. It's definitely a silver lining of the lockdowns and everything that people like me who are generally tend to stay at home get to come give talks at MIT virtually. But the sort of the flip side of that is that we sort of have some of those of us who have other things going on in our lives have a little bit less time to prepare for these sorts of things. So I hope you will be forgiving if I am over time or unprepared or stumbling around here. So let me do the best we can. As let's see. So here's my contents. We'll talk about conservativity, what I mean by that, and then what I mean by duels, and then we'll go on to try to build up towards a proof of that. And I'll stop after each of these 5 sections and ask for questions. But if you have a question that you sort of really needs to be answered right now, go ahead and interrupt me. So what do I mean by conservativity, first of all? The kind of conservativity that I'm talking about is sort of a two-dimensional conservativity. So conservativity for, and it's not sort of the category theoretic conservative functor sort of respecting isomorphisms property, but it's the logical sort of conservativity, right? So in logic, we say one theory is conservative over another if it's sort of an extension with additional structure that doesn't allow us to prove anything new about the structure we already had. So that it's sort of, we can freely use the richer theory to reason about the weaker, the more impoverished theory without changing what we can prove about it. And what I'm interested in here is a two-dimensional version of that. And so the kind of theory that we're looking at is what's sometimes called a doctrine or an algebraic doctrine, to be precise. And this is a kind of an algebraic structure that we can put on categories. You might call it an algebraic two theory. They're sort of often encoded in some way with like a two-dimensional monad or something like that. I'm not going to be very precise about that, what I mean by that, but just look at a bunch of examples here. So categories that are equipped with some kind of limits or some kind of co-limits, products, finite limits and co-limits, could even be infinite limits and co-limits. Categories with some kind of monoidal structure, monoidal categories, symmetric monoidal categories, braided monoidal categories, closed symmetric monoidal categories, Cartesian closed, compact closed, trace star, autonomous. We'll talk some more about what some of these words mean later on. So all sorts of different kinds of monoidal categories with limits, and sort of it could be combining these categories with monoidal structures and limits and so on. All of these are just examples of what I mean by an algebraic doctrine. And I'm going to consider 2 of these doctrines where one of them is included in the other one. So what I mean is that any D2 category is also a D1 category. So for instance, any category with finite limits is also a category with finite products. Any symmetric monoidal category is also a monoidal category, and so on. Now, whenever we have a couple of doctrines like this with one included in the other, I'll say that the bigger one is too conservative over the smaller one. So we have an adjunction. Whenever we have one algebraic doctrine included in another, we have an adjunction. So this right-hand functor U here says that is just what I said before, that every D2 category is also a D1 category. And then this has a left adjoint that sort of freely adjoins extra D2 structure to a D1 category. And the fact that this adjunction, that we have this left adjoint here, is what requires these doctrines to be sort of algebraic, but I'm not going to be very precise about that. And then two conservativity is we say that if the unit components of this adjunction, so given any D1 category, we map it to the free D2 category that it generates, and then there's a unit map from including C into the underlying D1 category of that. And if that's fully faithful, then I'm going to call this inclusion to be too conservative. So this isn't the terminology I used in the archive preprint in the current version. There I called it fully complete, which is something that I've seen in a few papers to refer to the situation. But I've come to think that that's actually not a really good terminology because it was originally came from the property of a particular model of a particular theory being called fully complete, and then a few people started using it in this other situation, which is related but not really the same. And it's not very evocative for a category theorist or logician who isn't familiar with this sort of type theoretic programming language things. So I'm experimenting with too conservative, but if anyone has better suggestions for what to call this relation between a pair of doctrines, I'd be happy to hear it. So why am I interested in this relation between doctrines? So in particular, it implies that any D1 algebra in a D1 category embeds fully faithfully into a D2 category, namely the free one that it generates, like right by here by the unit. But the converse of that isn't obvious to me, because full faithfulness doesn't cancel, right? So if I had a C which was embedded full faithfully into U of some other thing, and this is fully faithful, it doesn't necessarily follow that the unit map is fully faithful, even though there is a unique factorization here from UFC into UD. So why, and it took me a little while to understand why this stronger property of the unit being fully faithful is important. So let me try to explain a little bit about that. One reason to care about this is to use formal calculi for D2 categories to reason about D1 categories. So for instance, if we have a string diagram calculus for D2 categories, or we have a type theory that can be interpreted in D2 categories, we'd like to be able to use that to reason about D1 categories consistently. This sort of allows us to do that in a consistent way. So we can think about sort of various weakenings of the two conservativity property and compare it to what those would say. So firstly, supposing we just had a functor from C to some D2 category that was faithful, then that would imply that, well, we could use the D2 calculus, and if it allowed us to prove that two morphisms are equal, then they would in fact be equal in any D1 category by faithfulness, because we could interpret the D2 calculus in this category E, and then that would reflect back to C by faithfulness. But if it were just faithful, then there might be some morphisms that we could define. We could, with some calculus things, some things that we could write down, string diagrams that we could write down in the D2 calculus that wouldn't mean anything in C. A better thing to have would be that this map is fully faithful, and then any morphism that we define in the D2 calculus could be interpreted in E, and then by full faithfulness, it would give us a morphism in C. If we only had some arbitrary map here, which was fully faithful, then in principle, it might be the case that if I chose a different E, then the same formal string diagram in the D2 calculus might get interpreted as a different morphism in C by these two different embeddings. And that's what possibility is what's excluded by looking at the unit of this adjunction, because this is sort of the universal map from C into a D2 category. And if this map is fully faithful, then sort of any other map into UE factors through this. So we can conclude that no matter what E I interpret my D2 calculus in, it gives me the same morphisms back in C. It doesn't depend on the choice of E. So that's why we're interested in this sort of two conservativity property. Are there any questions about that idea?
Someone is asking, why too conservative rather than conservative, like just conservative?
Well, that's a good question. I don't know. Like I said, I'm open to other things. I mean, so conservative is, some people use conservative just to mean this, the faithfulness, or maybe sometimes I think maybe they use it to mean that this map is faithful, which is really sort of, which is actually equivalent to having an arbitrary one because of the faithful maps do cancel. Conservative also has a category theoretic meaning of a functor that reflects isomorphism. So if I just said conservative, maybe I might think that these functors were themselves conservative functors instead of fully faithful. I don't know. Maybe I should say that D2 is fully faithful over D1. I don't know. Maybe we could talk about it afterwards and see what people think. I'd be interested to hear more opinions.
Sure. Okay. Any more questions?
All right, moving on, I guess. So conservativity of duels, what do I mean by duels? So, well, first of all, what are duels for? Dual objects in a monoidal category have a lot of uses. One example of a use is to represent parallelism. So if we think of objects in our monoidal category as representing sort of data types or computation types, and morphisms as representing sort of functions that we could define in some kind of a programming language, then the dual of an object we can think of as being sort of a type of channels or continuations that we are allowed to pass an A value to, sort of functions that take an A as input in some sort of parallel world. And sort of the characteristic string diagram properties of duals are this sort of cup and cap. My string diagrams go down the page. I know different people write them in other directions. For instance, this sort of cap here that sort of takes nothing and produces an A and an A dual, I can think about that as creating a channel which accepts an A, so that's the A dual, and also starting a thread that listens to whatever is passed to that channel and then uses it. So I get an A over here in the sense that I can then go on and use that A, but whatever I do over here sort of has to wait for somebody else to pass an A value to this channel, and then it'll sort of go around and get used over here. And then the way I pass an A value to a channel is with the cup. Maybe this is where I have a channel and I have an A value and I pass that A value into that channel, and then it sort of goes on back and gets used. And so the bent string straightening or zigzag laws. So this one says if I create a channel and then I pass a value to that channel, that's the same as just passing that value directly into the thread that I was working on. And the other direction says if I have a channel and I create a new channel and pass its output directly to the channel I had before, then sort of that's the same as just having one channel and sort of passing it around. There are other uses of duals as well. They can represent input-output modes in logic programming, and of course, in category theory, they're used for various other things. But I wanted to mention this one particular application to programming. So we'd like to be able to sort of say that we can have channels or we can have duals as sort of first-class citizens in our programming language, maybe without sort of changing what the things that we can compute or the sort of computations we can do, or sort of give ourselves a way to evaluate such computations involving duals and sort of get back to a function that we started from. So that's sort of a question of conservativity. But the simplest sort of dual is actually not conservative. So this is the first sort of dual that a category theorist would learn about or think about, where we just have these as maps, sort of as sort of the direct interpretation of these cup and cap diagrams in a monoidal category with the ordinary monoidal category string diagrams. And then if I have a symmetric monoidal category with these duals, then it's called compact closed, and these are not too conservative over symmetric monoidal categories or closed symmetric monoidal categories, because they give us extra morphisms that we didn't have before, namely traces. And so a trace is what you get when you take the cup and you feed it into the cap, and you have to put a little twist in the middle, so that's why we have to be symmetric or at least braided. And in terms of sort of channels, you can think about this as a sort of a deadlock. I create a channel and then a thread listening to that channel, and then I take the sort of the output in that thread and I pass it as the input to that channel. So I'm sort of saying, well, this thread is waiting for the input and output of this channel, but this channel is also waiting for this thread to give it something to pass in and sort of never compute anything. And that's a sort of a new kind of morphism that we really don't want, so we'd like to sort of prevent that from happening. Compact closed categories are too conservative over traced monoidal categories. So this is sort of a side light here that we're not going to talk about, but it sort of basically means that these traces are sort of the only problem in the compact closed case. So the question is whether there's some kind of a weaker kind of dual that doesn't include these traces, and so that might be conservative over symmetric monoidal categories or closed symmetric monoidal categories. So in order to define that, I mean, some of those of you who know what a star autonomous category is already know the answer that I'm going to give, but I want to give a slightly different lead-in to what that kind of dual is, because it'll be useful later on. So let me go back for a minute and now review the notion of a multi-category. So a multi-category is a kind of category where we have Hom sets that have multiple objects as in the input. So you can, if you're a mathematician, you may like to think about multilinear maps. If you're a logician or a type theorist, you may like to think about this as a sequent with an entailment that has multiple things in the premises, multiple types of things in the hypotheses. I'm considering symmetric multi-category, so we have sort of exchange rules here. We can permute the objects in the domain of a morphism, and then we allow ourselves to compose them by taking any morphism and plugging its output into any of the inputs of some other morphism, as long as it's well typed. And that gives us a composite where the sort of the inputs are put together. And we also have an identity morphism, which only has one input and one output. And then there are associativity, hidden equivariance axes, and so on. So multi-category is basically kind of like a monoidal category where we don't have a tensor product anymore, but we have what would be the maps out of the tensor product. Now this doesn't have any notion of dual, but there's something similar we can define, which does have a built-in notion of dual. And this is called a star polycategory. And the particular ones, there are different ways of presenting this and different versions of this. The kind that I'm going to talk about are called entries only and symmetric. So symmetric means we can permute things, and entries only means that we don't put in we don't sort of distinguish between in sort of the definition. We don't distinguish between having the inputs and the outputs, because, and this sort of makes sense in sort of a world with duals, because whenever I have something with inputs and outputs, I can take one of the inputs and bend it around to become an output, or I can take one of the outputs and bend it around to become an input. So in this sort of entries only world, we just say, well, instead of a domain and codomain, a morphism just has entries. So a Hom set just has n things. If you're a logician, then you might like to think about this as sort of like a one-sided sequent, although it's actually closer to the way I'm thinking about it, to have the sequence be on the left than on the right. The way we represent the duals is that we equip the objects with an involution, which takes an A and goes it to some sort of formal dual object, A star, and we require this to be an involution, so A double star is actually strictly equal to A. You can weaken this to some sort of involution up to isomorphism, but that won't be important for us. And if I want to draw string diagram pictures for this, then I can draw this morphism in any of these ways. Because I have this dual object, I can think about it as taking any one of these objects and moving it back around to the codomain, like I did over here with a dual. So I can take my F, I mean, formally, it's just an element of this Hom set that has n entries, but I can draw it pictorially in any one of these ways by taking one of the objects and writing it, the dual object instead, as sort of the output, and keeping the others as the input. So there are n different ways to write a morphism of this kind. And I have permutation actions that swap these things around. And then I have a composition, which you can think of as in a couple of different ways, right? So if you're a type theorist or a logician, you can think about this as a cut rule. It's sort of saying if I can prove a bunch of stuff together with, or C, and I can also prove that either one of these things or not C, then I can do a cut and conclude that I get one of these other things, but no C's at all, which is sort of my output here. And if you're a category theorist, you might prefer to think about it in terms of composing together these pictures, where sort of I'm saying, well, I've got an F and a G, which an F has a bunch of A's and it has a C, so I'll regard that as going from all the A's to the C dual, because in sort of this way. And then I've got a G, which takes in a bunch of B's and also a C dual. And then I can compose that and I get something which takes in a bunch of B's and a bunch of A's. Right? So in order to compose things, I sort of choose one of the objects to compose along, and one of them has to have that object and the other one has to have the dual. So the notion of star polycategory was originally defined by Martin Hyland in a slightly different way, where you had both a domain and a codomain that was sort of separated in the definition. But this sort of entries only way of presenting it gives you an equivalent notion. Okay, now we'd like to be able to talk about monoidal categories as well as multi-categories. And in a multi-category, we can characterize when we have tensor products by a universal property. So this is sort of this universal map from an A and a B to a single object. to A tensor B. And that has the property that whenever I have a map with A tensor B in its domain, I can compose with this thing, and then I get an isomorphism between this Hom set mapping out of A tensor B and this Hom set that's sort of multilinear maps mapping out of A comma B and some other stuff. And if we have all these tensor products as well as sort of a zero array one, then we are in fact equivalent to having a symmetric monoidal category, because we have a symmetric multi-category. I'm looking at symmetric monoidal categories, multi-symmetric everything today. And we can do something similar in a star poly category. We can say, well, if I have one of these things, right? So remember, this is our star poly category way of saying that I have a morphism from A comma B to A tensor B. But of course, although of course it could also be a morphism from A and A times B star to B star or something like that. But this is how I'm thinking of it. And then I say that composing with that induces a similar kind of isomorphism here. Whenever I have an A tensor B, I can replace it by an A comma B by composing with this thing. So that's the same kind of tensor product. And whenever we have all of those in a symmetric star poly category, then what we get is called a star autonomous category. And you can define a star autonomous category in lots of different ways. You can define it as a monoidal category, symmetric monoidal category together with a dual operation function and some isomorphisms. You can define it as a linearly distributive category in which duels exist and all sorts of things like that. This is a particular one that I'm going to use today, is that it's a representable star poly category, symmetric star poly category. A general star autonomous category might not have strictly involutive duals. It might have only isomorphism, but today we might as well be strictly involutive.
Mike, I have a question. So am I understanding this right, that you actually have to have these isomorphisms quantified over all objects, C1 through Cn? And
yeah,
so
all C's and D's here and all C's here.
So there's no like coherence theorem, like if you know it for, I don't know, the first one or something, it induces it for the next?
Sorry, what do you mean by first?
Well, like, I mean, you can't just have it for like C1, A tensor B, and then you can show that it's true, like some kind of coherence theorem, like.
I mean, you can get away with a little bit less. Well, no, in fact, actually you can't, because I mean, in a general, I mean, you need to be able to say something, right? Because you want C to be a symmetric monoidal category. So you want to know that, you want to know that, say, C, the maps from out of some list of things into D are isomorphic to the maps from out of a tensor product into D. And in order to conclude that, you need to know something about the maps with arbitrary arity in the domain. And I don't think you can reduce that to any statement about something with smaller ones.
I see, thank you.
It's certainly, maybe I should say, if you, the sort of the simplest version that you might think about is if you just take n is equal to 0 and sort of like an ordinary unary map from A tensor B to D, equivalent to maps from A comma B to D, but that's not even enough to say that you have a symmetric monoidal category, because that's not enough to prove associativity. So if you just want associativity, then it might be enough to have fewer than n, but you'd actually like the whole thing to be equivalent to what you get. Okay, so a nice thing about, let's think a little bit about what a star autonomous category looks like. One thing we can say about it is that it's automatically a closed monoidal category, and the internal Hom is defined like this as the dual of B tensor C dual. And you should compare this with the situation in a compact closed category where it is in fact closed, and the internal Hom is B dual tensor C. And in a compact closed category, duals distribute over tensor products, and so these two expressions are the same. But in a star autonomous category, they don't. The dual doesn't distribute over the tensor product, and so this turns out to be the right definition of the internal Hom. And here's the proof that that is an internal Hom, right? So we have to say that maps from A into this internal Hom, right? And so that means a map whose entries are A and the dual of this internal Hom. We want that to be equivalent to maps from A tensor B into the dual of C, or into C, which is sort of the entries being A tensor B and C dual. And so I just sort of put in the definition of all these things, right? So the dual of this guy, because this guy is defined to be a dual, so its dual is just the thing inside here, B tensor C dual. And now I use the universal property of that tensor product and get B and C dual. And then I use the universal property of the tensor product A tensor B to put the A and B together. And so Astronomers kind of is also closed. It also has these sort of cup and cap morphisms, but they look a little bit different when you write them out in terms of objects. So the evaluation morphism goes from A star tensor A to the dual of the unit object, whereas the co-evaluation goes from the unit object to the dual of A dual tensor A. So you have to say something about how exactly to interpret those as string diagrams, and that sort of leads you into the world of sort of linearly distributive categories, and sort of the dual of the tensor product is some sort of other tensor product that's sometimes written like that. But in particular, what matters for us now is that this extra dualization means that we don't have a trace. So we can hope, at least, that the star autonomous categories would be conservative over, say, closed symmetric monoidal categories, even though compact closed ones are not. So that's my introduction to duals. Maybe I'll pause for more questions.
Oh yeah, there's a comment from the audience. So the viewers on YouTube will see the picture of your webcam on the top right corner. So please don't use that corner to write in your board, because it will be hidden.
Thank you. I will try. Is it sort of like this much?
Even less vertically. Like don't.
Something like that.
Yeah.
All right.
Yeah.
I'll do my best to avoid that.
Something like that. Very good.
Okay.
There's another question. Sorry.
Yes. Go ahead.
So somebody's asking, in motivating the conservative map, why do we want to prevent extra morphism traces and so on in the first place? Is it because the type system gets more complicated and harder to control?
Well, there are a lot of different reasons, and I'm not saying that everybody will always want that. I mean, different people will want different things for different reasons at different times. But what I would often like is to be able to freely use the type system or the string diagram calculus with duals and sort of draw pictures like this and sort of more complicated stuff with cups and caps and bent strings and straighten them around. And not worry about whether I might accidentally be writing something down that doesn't actually mean something in the world where that I care about, namely the D1. So for me, I'm starting with, say, a closed symmetric monoidal category or a Cartesian closed category even, but I'd like to be able to represent its internal hums with some nice sort of type theory that involves duals or string diagrams, and not have to worry about whether there's sort of extra stuff in there that I don't care about. In some other situation, you might not worry about that. You might say, well, I have these new things that are deadlocks, but I'm just going to sort of hope that I don't ever end up with one, and sort of just use it to reason about the things that I started from. So you can get away in some contexts with not worrying about that, but it sort of makes us a lot freer in using the richer calculus if we have this conservativity. I hope that gives some kind of an answer.
Thank you. And another question is there a nice string diagram calculus for these poly categories with duals?
For the star autonomous ones? Sorry, it's just, I didn't hear what you said. Is there a nice string diagram calculus?
Poly categories with duals.
Poly categories with duals. Yes, absolutely. It's this sort of same thing. I mean, you basically, like a morphism, you can say something like this. You just sort of dualize all the things down here and not all the things up here.
All right.
Okay, so go on.
Yep.
All right. Okay, so let's think about how we can prove conservativity of one doctrine over another. And there's a very general way of doing this, which was, I believe, due to Lafont, which uses the Uneda embedding. So the Oneida embedding, which I'm writing with this yo symbol from some Japanese my alphabet, is often gives us a way to take a D1 category and embed it fully faithfully, right? So this is the Oneida embedding is fully faithful, embedded in some D1 category, namely its pre-sheaf category. Right? We're not, this isn't the free thing in general. It might in some cases be, but rare, but in general it isn't. But it also is very good. It has lots of stuff. It's complete and co-complete. It's Cartesian closed. It's a topos. And this embedding preserves all limits and Cartesian exponentials at least. In the monoidal case, we have a day convolution structure on the pre-sheaf category, and the Oneida embedding preserves it. So if D2 involves any of this stuff, then the Oneida, the pre-sheaf category is a D2 category, and the embedding preserves it. That doesn't work when D1 involves some co-limits, but what we can do in that case is just restrict to some subcategory of the pre-sheaf category consisting of the pre-sheaves that preserve those co-limits. So a pre-sheaf, right? A pre-sheaf is a functor from C op to set, and so those co-limits are limits in here in C op, and we take them to limits in set. Those are the pre-sheaves that live in this category Pi of C. And then this embedding here also then will preserve those co-limits. So this trick is sometimes attributed to Kelly. So in lots of different situations, we can embed a D1 category in a D2 category by using its Oneida embedding. But as I said before, that isn't quite true conservativity, because this thing, the pre-sheaf category, isn't in general the free D1 category, D2 category generated by a D1 category. But Lafont came up with a trick to enhance that to conservativity using a gluing construction. So let me describe this in sort of a general framework, or sort of a general context, without being precise about exactly what D1 and D2 are. I'm just sort of going to state the things that have to be true to make it work. So suppose that PC has the pre-sheaf category has D2 structure, and within take this comma category. So this is the Oneida, this is the pre-sheaf category. This is the identity functor, and then this is the free FC is the free D2 category generated by C, our D1 category, and then this Oneida sub eta is the restricted Oneida embedding. So it takes an X is in FC, and then A is in C, right? Because it's this thing is supposed to be a pre-sheaf on C, so I have to evaluate it at A. And that gives, I just sort of map A into FC by eta, and then I take the Homs in FC, so the restricted Oneida embedding. And then we take this comma category of the identity functor over this guy. So the and then usually this is sometimes called a gluing category, or Artin gluing, and usually this comma category is also a D2 category. This is, and these projection functors are D2 functors. And that's true even though this restricted Oneida embedding is not generally a D2 functor, because of the sort of the laxness of the comma category makes that work in most cases. Okay. And then we get a functor from C to the gluing category, which I'm calling theta. And so how do we define that? Well, an object of the gluing category is a pre-sheaf together with a map from that pre-sheaf to Oneida eta of some f of C. And a fancy way of saying that is that the comma category has the universal property that maps into it are equivalent to giving natural transformations like this. A pair of functors into FC and PC together with natural transformation. And so I'll take these functors in this case to be just the Oneida eta and the regular Oneida embedding of C into its own pre-sheaf category. And then what I have to give here is a natural transformation from the Oneida embedding of some object B in C to this composite, Oneida eta composed with eta of B. And I have a component that is, so this is a pre-sheaf. I have to evaluate it at some value A. And so what I'm starting from here, the definition of the Oneida embedding is I'm starting from the Hom set from A to B. And if I compile out what this means that I'm taking Oneida eta of B, but by definition of Oneida eta, that means that I'm applying eta to A and then mapping out of that into this guy, A to B. And so this is just Homs in Fz from A to A to A to B. So this is just the action on Homs of the functor eta. I have a map from here to here, and that gives me this 2-cell, and that defines my functor theta into the glued category. And usually this is a D1 functor. C is a D1 category, so I can't expect this to be more than a D1 functor, and usually this is a D1 functor. And now we do this, one of these sorts of, we use the universal property. So somewhere we have to use the fact that FC is the free category, the free D2 category generated by C. And this sort of building of G is sort of giving us a way to apply that universal property in a useful way, because G is a D2 category and theta is a D1 functor. Right? So this is a D1 functor into a D2 category, and eta is the universal D1 functor into a D2 category. So I get this unique factorization by this functor omega from f of C to this glued category G. By the universal property, sort of this is a section of the projection back down to f of C, because when I compose it, right, this projection is also a D2 functor. So when I compose it with that, I get some D2 functor, which sort of has to be the identity by the universal property of eta. So now let's look at what this omega does on Hom sets. It's a functor, and I have to, so it has to act on Hom sets. So it takes, and in particular, let's look at the Hom set from eta of A to eta of B, because that's what I care about to ask whether eta is fully faithful. Okay, now this is going to map it to omega. This is going to map it to the Hom set in G from theta A to theta B, because this triangle commutes here. Right? So I've taken eta and then omega. That maps these objects have to go to theta and theta. And now the definition of theta is that it consists of eta and uneta and the action of eta on Homs. Right? So these things here are the action of eta on Homs. And now I've got to give a morphism in G from this theta of A to this theta of B. And so that has these 3 components, or we have 2 components together with a commutative square. This first component has to be the morphism in FC that I started from. It's a map from A to A to A to B, and it has to be H because omega is a section of this projection. The second morphism is a map between representable functors. So the uneta lemma tells me that it's uniquely determined by a map from A to B, namely something that I'm going to call omega bar of H. And then this commutative square tells me that if I take omega bar of H, which is a map from A to B and C, and I apply the functor eta to it, then I get my object, my morphism H that I started from over here in FC of A to A to B. Okay, so exactly what this section does is it tells me, given a morphism from A to A to B, I produce a morphism from A to B, which maps onto it by eta. And so this is precisely saying that the functor eta is full. And in fact, eta is faithful. You can get this in an easier way, but you can also get it directly from this by saying, because omega composed with eta is theta, that essentially compiles out to meaning that omega bar of eta of G is equal to G, that we get back to where we started from. And so we have a pair of inverse isomorphism. We've essentially constructed an inverse to the action of eta on Homs, so eta is fully faithful, which is what we wanted. With these 2 is too conservative. Okay, so that was a long, complicated argument, but I wanted to go through it because I think it's deserves to be better known that you can sort of prove this sort of fact using this gluing argument. I had a little bit of trouble tracking down actual proofs of this, so I kind of wanted to share it. So in summary, what this technique requires that we need D1 and D2 to lift to common categories, so that in some coherent way so that it all works. And then we need that input place that the presheaf category has to have D2 structure and the uneta embedding has to be a D1 functor. And we can, if we have colimits, then we can restrict to the presheaves that preserve those colimits instead of all the presheaves, and it still works. But it doesn't work in the case of duels, right? So we're going to have to change it somehow to deal with duels. And the reason is that among all those good properties of the presheaf category, being star autonomous was not one of them. So we're going to have to do something slightly different. So that's, now we're going to move on to some kind of other kind of innate embedding, but maybe I'll pause here for questions.
Okay, so a question is, the restricted uneta is a D2 functor, but the projection from the glued category to the perceived category is? Question?
That's right. The restricted uneta embedding here is not a D2 functor, but these projections are D2 functors. And in a lot of cases, this restricted uneta embedding is sort of a lax D2 functor. And that is sort of what makes it work. This is what I meant by abstract nonsense here, that I didn't say this verbally. Right? So algebras for a two-monad have the property that when you take a comma object of a colax functor over a lax functor, then you end up with another algebra, and the two projections are in fact strict or strong D2 functors. So this is sort of a nice property of lax and colax morphisms. This sort of two-monad thing doesn't always apply, like in the closed cases, but often this sort of abstract nonsense is what makes that work. So you should think about this as sort of being lax, and that's sort of what makes it happen. Any questions?
I see. There's another question. It's two more towards the end.
Yes.
Is that gluing construction a sketch of a proof, or can this be carried out as a precise argument in some generality?
I have not seen this argument written down in a general form of the sort for any two monads at D1 and D2 or blah, 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 or for any something or other. I've only seen it written down for particular pairs of doctrines, D1 and D2. And this is sort of a sketch of how those proofs tend to go. I would be surprised if there were not some way of writing it down in generality, but I haven't tried to do that, and I haven't seen it done. That doesn't mean that someone hasn't done it. I don't know, maybe someone has.
I see. Okay, I think there are no other questions for now.
All right. So what we need is some kind of replacement of the uneta embedding that will work for duels. So to sort of explain and motivate that, let's talk about how our star polycategories are related to multicategories. So first of all, there's a forgetful functor from star polycategories to multicategories, where I just do the intuitive thing. Right? So I give a multi-map from a bunch of things to a B. I'll just take the entries to be those A's and the dual of B. I don't know if I had to move that down. People can see it online on YouTube. Okay, so now this functor has a left adjoint that takes any multi-category and makes it into a star polycategory in a free way. And the way we do this is every object, we sort of equip it with a formal dual, which I'm going to write as A bar to distinguish it from the dual operation. So the objects of L of C are two copies of the objects of A, and the involution is sort of what you would expect, that every object dualizes to its formal dual and back again. And the Hom sets of this star polycategory are empty unless they contain exactly one of these formal dual objects, in which case we can define it to be the Hom set in C, where that object appears in the codomain. And then that allows us to define composition from C, sort of use the composition in C to define this operation. So we'll come back to this left adjoint in a minute, in a few minutes, but right now what I care about more is the, so let me skip that for now, is the right adjoint. Okay, so there's also a right adjoint, and in this case we sort of dualize things. Instead of taking the coproduct of the objects of C with itself, we take the product. So an object of R of C, this star polycategory, is a pair of objects of C, which I'm going to write as A plus and A minus. And then the involution just swaps those two objects. It goes to A minus A plus. So you can think about it on objects. What's going on is these are just the left and right adjoints to the forgetful functor from sets with involution to sets. Right? So this has a left and right adjoint. This is just what we're doing on the objects. And then we're extending it to the morphisms in sort of a way that works. And the way it works on morphisms here is I want to give a morphism with some entries A1 and AN, and now what I can do is I can pick any one of those to be the codomain, and I sort of make all possible choices, and then I use the negative object to be when I'm looking at the codomain. So I take morphisms from all the objects except one of them with their plus components, which are objects of C, and then I take the minus component of the other missing one and put it in as the codomain. And then I do that for all possible choices of which object to do that with. So there are n factors here. So a morphism in R of C with n entries is n different morphisms in C. And in particular, a morphism like this, so a morphism from A to B in R of C, right? This is how we represent that, where A and B star, remember using the dualization, consists of a morphism in the forwards direction from A plus to B plus, and a morphism in the backwards direction from B minus to A minus. So in other words, the underlying ordinary category of R of C is just C cross C op. And then we can induce composition from C in a similar way. So those of you who have seen something called the Chu construction may recognize this as the Chu construction applied where the dualizing object is the terminal object. And in fact, we can see the more general Chu construction in this light if we talk about instead what you might call an augmented multi-category. So by that, I mean a multi-category, a symmetric multi-category in our case, which is additionally equipped with Hom sets that have emptied codomain. And so you can draw those as sort of a morphism with some things coming in and nothing coming out. And then we have sort of the compositions that you would expect. Like I can take one of these guys and then I can plug a G into it. Oops, I'm up in the no writing zone there. I can take one of these guys and I can plug a G into it that has one output and a bunch of inputs. And then I get another one of these guys that has no outputs and a bunch of inputs, and so on. So for example, the case where this usually happens is if I fix some particular object of C, which I'm going to call bottom, and then I can pair it with C to give myself an augmented multi-category where I just C comma bottom, where I define the morphisms with empty codomain to be just the morphisms in C into this specified object bottom. And in that, now I have a forgetful functor from star polycategories to augmented multi-categories as well, where I just sort of take these things with empty codomain to be just the Hom sets of E in the ordinary sense. And this also has a right adjoint, and this right adjoint is in fact literally the ordinary Chu construction if I apply it to this augmented multi-category produced by this dualizing object bottom. The Chu construction is usually described as a star autonomous category, and in fact you can show that if your augmented multi-category is a monoidal category, so it has tensor products and it also has some pullbacks, then in fact the thing that you get here is a star autonomous, so it has these representing tensor product objects. But more generally, you just get a star poly category. So so we have ways to get from an augmented multi-category to a star autonomous category or a star poly category, and that's what we're going to use to make our improved Uneda embedding. But now we need somewhere to start from. So where do I start from? So suppose I have a star poly category. I want to make some kind of a Uneda embedding for it. And so one natural way to approach that is to say, well, fix a particular object of E and then ask, what are sort of the Hom sets into E look like? And what they look like is, well, I can take any other collection of other objects and then I get a set. So this sort of Uneda representable object of B can be whatever it is, it can be evaluated at a bunch of other objects and give me a set. And so Martin Hyland abstracted away from this to describe what an E module is for a polycategory or a star polycategory E. And it consists of a bunch of sets which are associated to any list of objects, which have permutation actions and also compositions or actions by morphisms in E, right? So you can think about this as like the action of morphisms in a category on the presheaf, on a presheaf M. It's just that a presheaf is now getting evaluated on a list of objects instead of a single object because we have a polycategories instead. So we have this notion of module, and we have these representable modules that look like this. And we also have this thing which you can call the tautological module, which is sort of representable by nothing, that you just evaluated on a bunch of objects. You just take the Hom set of all those objects. And this is sort of a new thing in the world of polycategories, that ordinary categories don't have sort of a tautological presheaf in a sense like this. And that is going to turn out to be important. So this is the Uneda embedding. We put all that together for multi-category, polycategory. The modules from a multi-category with the multi-maps that look like this. I'm getting a little bit low on time, so I'm not going to say exactly what that means. And then we have, in fact, it's an augmented multi-category. We can augment it by this tautological module. So the empty domain morphisms are the maps into this tautological module E. And then the representable functors give us a map, representable modules give us a map from the underlying augmented multi-category of E into this thing, this EMOD thing coming from, with its tautological module E. And now we can use, we have this adjunction, right? V plus is left adjoint to the Chu construction. So whatever this Chu construction is, we get a map from E into the Chu construction of EMOD at the tautological module E. And this is what Martin Hyland called the envelope of our polycategory E. It is in fact closely related to the Isbell envelope, if you know what that is. So it's a reasonable terminology. And Hyland proved that this Uneda embedding is fully faithful. And the envelope category is star autonomous, so it satisfies these representability conditions for the Chu construction. So this gives us a way to take any star polycategory, or any polycategory in fact, although I just did it in the star case, and embed it fully faithfully into a star autonomous category, one which has these tensor products. And that was what Hyland wanted to do here. And it's a very Uneda-y kind of embedding. We just have to do this module thing, kind of Uneda embedding for a polycategory is slightly different from an ordinary category. And then we do this funny sort of right adjoint Chu construction to sort of move it back into the world of polycategories rather than multi-categories. The only change we're going to have to make to that is that we might want to consider the modules that preserve some collection of tensor products. And this is just like the sort of the Kelly trick that I mentioned before, where you can look at the presheaves that preserve some colimits. Here I can look at the modules that preserve some tensor products. So a module lives in this subcategory of modules if there's an induced isomorphism here composing with the module with the universal property, universal morphism, and then we take the Chu construction of that, and this gives us a restricted envelope. And as long as these are actually tensor products in the thing we started from, then we can embed a star autonomous category. We can embed this E into some star autonomous category of the sort of restricted embedding, which preserves these tensor products. So if I start from a symmetric monoidal category, then I can take the tensor products in that symmetric monoidal category and map them into this LC, which is a star polycategory, and then apply this restricted Uneda. So this gives me a way of embedding, say, a closed symmetric monoidal category or symmetric monoidal category into this star autonomous thing here. So I'm actually running a little bit low on time. So I probably won't get to say in detail everything that I wanted, but I should probably pause for questions here.
There is one. What is a good reference for this fact about lax morphisms, co-lax morphisms, and comma objects? The abstract nonsense that you can sometimes use to prove that the Blooming category has the right structure.
So the references for that are, there's a paper by Steve Lack, which is something like limits for lax morphisms. Where he talks about limits involving strict morphisms and lax morphisms. And then he and I generalized that to completely characterize the exhibits that limits that lift to lax morphisms. And I don't remember the name of that paper, but you can find it on my website. It's the only paper written by Steve Black and Mike Shulman. And the version for an op-lax functor and a lax functor, I don't actually know if that's written down anywhere. It's kind of difficult to state exactly even what the universal property of it in that case is. It has something to do with double categories, but I think it hasn't really been worked out completely. But it's a similar sort of argument to show that it exists, at least.
Okay, thank you.
Okay, so I've got like 1 minute, maybe, because I should stop a little early in case people have more questions. Let me just say that we can basically, now we have this kind of embedding, this envelope embedding. We can do the same sort of Lafont gluing construction. So here's our, whatever this is, a star polycategory, or it might be LC coming from some monoidal category. And we embed it into this free star autonomous category. And then we do this, basically the same construction where we take Yoneda embedding into this envelope category. We have to modify it slightly. Instead of taking the ordinary envelope here, we change the dualizing object to be sort of the restricted Yoneda version of the ordinary dualizing object here. And then we sort of have to take what's called a double gluing construction, which means that instead of taking the ordinary comma category of these sort of star polycategories or star autonomous categories, we use what's called a double Chu construction here. So that, which basically means that we want the morphisms that are the data in the gluing category not to be these sort of Chu morphisms, but just to be pairs of morphisms that are both going in the same direction. I don't want to try to go through all of that precisely. I should attribute this notion of double gluing to Hyland and Tan and Schalk. I don't actually know where this was first written down, but there's a paper by Hyland and Schalk that describes it, and then some people say something about Tan's thesis as well. Well, I haven't read that myself. They didn't describe it in terms of double categories, but a little bit more explicitly. But it basically is the correct kind of gluing for star autonomous things or star polycategory things. That maybe I'll stop there. So here's the paper. You can look up all the details there. I'd be happy to talk about them later in questions. Thanks.
Thank you very much. All right, are there more questions? Well, in the meantime, I have one. Actually, I'm curious about your Vista slide. Can you maybe say a little bit about it?
Sure. So the first one is that we can do this to other things too, right? So I didn't say my main goal was to do it for a closed symmetric monoidal category. And in that case, we can do this LC thing to it, which gives us a star poly category. And then we can embed that in the free star autonomous category. But you can do this to other kinds of star poly categories, and you can start from a linearly distributive category instead, if you know what that is, and get another Chu conservativity result. And you can also include limits and co-limits as well as tensor products by doing the sort of exactly the Kelly trick on your modules. The caveat is that when you start with a monoidal category instead of a poly category, you can only use non-empty limits and co-limits because the initial and terminal objects aren't preserved by taking C into this LC thing. In fact, it actually fails in that case. Schelling's proved that star autonomous categories with initial objects are not conservative over closed symmetric monoidal categories with initial objects. Logically, that says that classical linear logic is not conservative over intuitionistic linear logic as long as you have the zero, the initial object, the additive falsity. So in some sense, this result here about the non-empty limits and colimits is the best that you can expect.
I see, thank you. So we have a question too, actually. So one says, in those algebraic manipulations of Hans, I lost track about how this relates to parallelism. Talking about the motivation part. There we got the intuition that star is about creating channel types. Does this approach relate to the existing pi calculus approach to processes studied by some type theorists?
You broke up a bit when you were saying what it was, asking what it was related to. Can you say that again?
Sorry, yeah. Does this approach relate to the existing pi calculus approach to processes studied by some type theorists?
That's a good question, and I don't know the answer. What you can sort of take this idea of this envelope construction, and you can sort of say explicitly, if I start from, say, a Cartesian closed category or a post-symmetric monoidal category, you can say, what does this envelope look like? And what do these representable objects look like? And what do their duals look like? You can say things like the dual of a representable is sort of carries all the information about all the morphisms that you can get that involve that object as an input. Sort of it encapsulates all of those, all the ways to use an element of that type. I kind of suspect that a calculus that's built directly on processes, I don't actually know anything about the pi calculus, but does it prevent you from getting traces and deadlocks and things like that? Or is it sort of a more general compact closedy sort of thing? There's something to think about. If you have a calculus, which could be, I mean, one thing to say, right? So I don't know, there are all sorts of different calculi that you could have for talking about processes. But if you have a process, if you have one calculus that can be interpreted in the star autonomous category, then the point is to say, well, you can interpret that in, say, the envelope or in the free whatever, and thereby anything you can define in that calculus can be compiled back into something in, say, ordinary lambda calculus without a basic notion of process. So in a way, I guess it is a way of talking about whether or not a particular, gives you a semantic way of saying whether a particular calculus for processes is sort of giving you new stuff that you couldn't do before, or whether it's just a sort of more expressive way to talk about the stuff you already had.
Could I ask a question?
Yeah, sure. Go ahead. Let me just say that the paper of this talk and the one together with Steve Lackner were mentioned are linked in the Zulip channel, thanks to Max New. Please go ahead.
Thanks, Mike. This is really great. I'm wondering how much of this gluing construction is truly like a two-categorical or two-algebraic phenomenon, and how much of this maybe could be used back for one conservativity of one theory is maybe taking the power set instead of presheaves or ideals in various senses.
Yeah. So so if you're talking about algebraic structures on posets rather than on sets, which is sort of the 1,2 theories, you might say, then I would expect all of this sort of stuff to happen in about the same way as it does for two theories, for categories. You would take your sort of, as you said, you would take your sort of ideals or downsets as your presheaves, and then your comic object and so on. It's just that all your morphisms would be inequalities rather than Hom sets. If you're actually going down all the way and talking about algebraic structures on sets, then I don't think you need any of this structure because the notion of conservativity for that is cancelable. So what I mean is, sorry, let's see. If you, I said this briefly before, like if you have your C and you map it into f of C, and then you map it into some u of E, and then you have the unique map here, right? So if you know, as soon as you know that this map is, say, injective, then it automatically implies that this map is injective. And so similarly, this is the easier way that I mentioned to prove faithfulness, because faithfulness also cancels. If you know that this map, this is a functor that is faithful, it automatically implies that this functor is faithful. And similarly, if this functor is conservative in the sense of reflecting isomorphisms, then this functor is also conservative. The only reason you need all this extra gluing nonsense is because this doesn't work for fullness, because that doesn't cancel even in the presence of faithfulness. So yeah.
Thank you.
That's something that I don't really fully understand, is sort of the interaction of all this stuff, but it's interesting.
Thank you. There's another question. What was the original thought process for trying the gluing construction again?
By the original thought process, do you mean what the font was thinking, or what I was thinking, or so? I mean, there's a general principle, I guess you could say, that goes into lots of these gluing constructions, which are used for all sorts of things. Which is that you have some object here, which is essentially characterized by a mapping out universal property, and like I say, it's free. There's, like in this case, it's freely generated by C, or maybe in some other cases, it's the initial category generated by syntax or something like that. And you want to prove some concrete thing about this object, like in this case, that its Hom sets are bijective to the ones you started from in C, or maybe in some other case, you want to prove canonicity or normalization for a type theory, or some sort of parametricity fact for a type theory, or so on. All of these things can be proven by similar sorts of gluing constructions. So what you need to do is somehow you need to say, well, I need to build some object such that mapping out of f of C by using its universal property tells me something about f of C itself. And so that's the idea going into this gluing construction, right? You sort of say, well, I want to say something about the Hom sets of f of C, and so I need to build some object that I can map out of it into that knows something about those Hom sets. And so what are those Hom sets? The Oneda embedding knows something about those Hom sets. And so this, and so I could sort of say, well, there's going to be, I could map into the Oneda, I could map into this guy by using the universal property, maybe directly, but it doesn't quite that doesn't tell me enough information, because it's only using the existence aspect of the universal property. I also need to use the uniqueness aspect to expect to be able to say something precise. And so sort of giving me an object living over f of C, so that I can use that universal property to get that this is actually a section of the projection, is a useful way to do that. There's also a syntactic way of describing a gluing construction, if you which involves this thing called logical relations. That if you think about the objects of the gluing construction as sort of something in f of C together with a presheaf, say R in P of C, and a map from R into this sort of restricted Uneda of X, then you can think about this as saying, well, it's every object X, so the objects of G are objects of X equipped with sort of a predicate, right? If this is a monomorphism, then it is a predicate on arrows into X. And this is sort of called a logical relation. And I guess since it's a predicate on arrows into X with arbitrary domain, or domain coming from C, sometimes it's called a Kripke logical relation, because sort of presheaves are called Kripke models by logicians. And so there's a syntactic way of approaching this that doesn't involve saying words like category and gluing construction, where you say, I'm going to sort of induct over the objects of f of c and use them to define a relation on each object, which is essentially what this section is doing. Because it is a section, it's defining, like, for every object of for every object of f of c, it's defining an R which lives on that object here, lives on that object, and the sort of the logical relation of that object. And so that's sort of the syntactic way of doing it. And then so you're a category theorist and you stare at this thing for a really long time, and eventually you figure out that what they're really saying is that it's a comma category. So there's different ways to approach it.
We have another question. Is there a way to say something like CT is conservative over PA, or an analogous statement that's actually true, by saying some category is conservative over another?
By CT and PA, what do you mean?
So yeah, can Brian Pinsky please clarify what do they mean by CT and PA?
PA could be piano arithmetic, maybe? I don't know. Is that the sort of thing you're thinking about, logical, like one theory is being conservative?
Conservative truth and piano arithmetic.
Okay, I don't know what conservative truth is, but I don't know of any way to express logical theories of that sort as categories in this sense. It could be that there is a way, but I don't know offhand what it is.
Okay, someone's asking, could you please show the page with the archive link again?
It's on my website too.
It is, and it's also linked on Zulip. Okay, from the previous question, a clarification. I forget, it's maybe computational truth. It's PA plus a truth predicate that satisfies induction.
Okay. I mean, I think that's, I mean, those are one theories, so they're more in this sort of situation. I don't know, sorry.
Okay, are there more questions? All right, seems we don't have any more live questions, so thanks to Mike again. That was a great talk. People are writing some appreciations across the channels.
People clapping in their video.
Also, yeah.
Thank you.
They're virtually clapping.
Yeah.
All right, if you have any more questions, you can ask them offline on the Zulip channel. So we are now having breakout rooms for whoever wants. So if you want to leave, of course, feel free to leave. If you want to stay over for more like in-person chat and get a cup of coffee or something, please stay in the call. And if you're connected with YouTube, you're welcome to connect to Zoom and join us for the breakout rooms, right? For now, I'll stop the live stream.